In calculus, we often define functions as continuous, meaning that there are no gaps in their numbers. In terms of a graph, this definition means there are no breaks, holes, or vertical asymptotes. For example, in this little graph, there is a hole at C, therefore it is not continuous. The graph of a function f is continuous if it meets these three conditions below. First of all, f of c has to be defined. The limit as x approaches c of f of x must exist, as well as the limit as x approaches c of f of x equals f of c. If it does not meet any one of these three conditions, then it is not continuous. For example, here we have three graphs. Graph number 1 is continuous, as there are no breaks, gaps, or vertical asymptotes in this straight line. However, if we go over to graph 2, we see a hole at what would be about 1 or any f equals c. It's not continuous at f equals c, therefore it is not continuous. Here, there is a jump between these, and they are not continuous either, as there are more holes. We also define continuity on other types of intervals. For example, if a function f is continuous on the interval a to b or a to infinity, if it is continuous at every number greater than a, and if, in addition, f is continuous from the right at a, for intervals on the form a to b or negative infinity to b, we require continuity of every number less than b in the interval and also continuity from the left to b. Using these facts, we can prove the following. If two functions f and g are continuous, the sum f plus g is continuous, the difference f minus g is continuous, as well as the product fg and the quotient f over g, provided g is not equal to 0, are all continuous. Now we move on to the intermediate value theorem, which is used throughout calculus. The intermediate value theorem states that as x varies from a to b, the continuous function f takes on every value between f of a and f of b. If the graph of the continuous function f is regarded as extending in an unbroken manner from a to f of a to the point b f of b, as illustrated in this then for any number between f of a and f of b, the horizontal line with y-intercept w intersects the graph in at least one point p, which would be here. The coordinate of this point p is a number such that f of c equals w. This can be used to prove many things, such as zeros of a function. Now for some practice examples. Classify the discontinuities of f as removable, jump, or infinite. In the first example, we see that this is not continuous, as there is a hole and a break. But what kind of discontinuity is it? It is a jump because there is a gap between here and here. In number 2, it is also a discontinuous function, but it is removable, as this has been removed from here, even though there is an f of c does not equal the gap. In the number 3, this is infinite, because no matter how high the numbers go, they will never reach each other and they will never touch. Therefore, there will always be discontinuity at this vertical asymptote.